Okay, we'll begin where we left off, right. The last time we had this structure where we had a 10 volts plate on the top and we had a 0 volts plate at the bottom, and we wanted to just use the difference method to solve for the voltage, right. So, we began with the algorithm, but did not have time to go over it completely. So, I will go over the algorithm fully and then we will start an octave code to solve for the voltage in the capacitor. So, what we knew last time was that the top plate was at 10 volts. So, the plate here these points were at 10 volts. The remaining points, the voltages are not known to us. The bottom plate is going to be at 0 volts. We have divided this region into a number of XY grid uniformly sampled, right, and we started to begin, alright. So, what we would do is we will come to the first point where we do not know the value of the voltage. It was originally 0, but we look at the neighboring points, 10 volts on the top, 0 volts is what we had initialized to the right, 0 volts at the bottom, and on the left hand side there was no point. We assumed that if we are not aware of the voltage at any point, we are going to make it 0, alright. So, the left hand side, since there is no point, we make it 0 volts, and this particular boundary condition is known as a Dirichlet boundary condition. It is a special boundary condition that we are using here, that the boundary is going to be having the unknown value equal to 0. So, it became 10 plus 0 plus 0 plus 0 divided by 4. So, we marked 2.5 volts at this point. Then we went to the second point, where we needed to estimate the voltage. We started at this point. So, that will be 10 on the top plus 2.5 plus 0 divided by 4, and we keep going to the next point. So, here it will be 10 plus 0 plus 0 plus 12.5 divided by 4, the whole thing divided by 4, and we keep going along the row. And once you finish that particular row, on the right extreme, once again we do not know the value of the voltage to the right side because there is no point over there. So, if there is an unknown voltage, we consider that to be 0, right. Once you finish the first row, you will go to the second row, you will keep going to the third row, and you will keep going till you reach the last unknown point. But while we are doing this, something has happened. When we began computing the voltage at the first point marked 2.5 volts over here, the right hand side point over here was at 0 volts. That is how you arrived at 10 plus 0 plus 0 plus 0 divided by 4. But now it has a voltage of 12.5 divided by 4. So, you began with something, but you ended up with something else, alright. So, we need to rectify this. So, now what the algorithm will do is, when you go from top to bottom for all the unknown points, we will say that we have finished one iteration of the calculation, right. So, we will go to the second iteration. You will start over here, you will once again compute the average of all the neighboring points. So, you will have 10 plus 12.5 divided by 4 plus whatever you had computed in the previous iteration. Left hand side there is no point, so we are going to assume it as 0 and divided by 4, and you keep doing this across all the rows, alright, going from top to bottom. That will constitute your second iteration. Once again you have to go to the top and start doing this all over again, and you keep repeating this till between successive iterations the value of the voltage at a given point does not change significantly. Okay. Now, how do we determine what is significant and what is insignificant? Well, it depends on the application. If you wanted to know the voltage distribution inside the capacitor to some precision, say that you need to know about 50 millivolts or 500 millivolts, that is the accuracy you need, you do not need more than that, then you set that as the error. If you want extremely precise calculation, then you say that let the error be very small, like 1 nanovolt, etc. Alright. Now, as you set the error between consecutive iterations to be smaller and smaller, we know that the number of iterations that you need to perform will become larger and larger and larger. Okay. So, that is the downside. That the other thing is it is perfectly controllable, right. I hope you are able to follow the algorithm now, and we will just fire Octave on the computers and write the programmatic version for whatever we have done now, right. So, I will start Octave. I begin all my programs with close all clear all and CLC command. Alright, close all will close all active figure windows and any other windows that have popped up in the previous run. Clear all will clear the variables in the workspace. So, there will be no variables in the workspace, the memory will be freed. CLC will just clear off my display buffer or the command window over here. So, I start all my Octave programs like this, you could do the same, right. Now, I need to define my voltage matrix, all right. V is going to be zeros of 30 comma 30. What this does is it creates a 2-dimensional matrix filled with zeros, all right, and the size of the matrix is going to be 30 rows by 30 columns. Okay. Now, one of the things that we saw in the algorithm was, as you start computing the value of the voltage, you have to compare the current value that you have calculated to the previous value that you had calculated in the previous iteration. That means, you need to store the current and the previous value, all right. So, I am going to make a distinction on the voltage, I am going to call this as V now. This means that the voltage that I am calculating now in the current iteration is going to be stored in V now, all right, and I am going to create one more voltage variable, all right, V previous. Right. Since I have zeros for all the values, I mean all the rows in the columns, just made it zeros of 30 comma 30. Okay. So, I will just run it for the sake of completeness. So, on the left hand side, I am having a workspace which tells me that I have two variables defined, V now and V previous. Dimension is 30 by 30 and I can check the values and it is going to be zeros for all the rows and all the columns. Okay. Now, I want to set the voltage at the top of this capacitor configuration to be equal to 10 volts. Okay. So, I am going to say that V now of what this one does is it takes the declared matrix from line number 2, takes the 30th row of that matrix, colon represent all columns in that particular row and I am going to set that to value 10, right. So, just makes an equal to sign. So, V now of 30 comma colon is going to be equal to 10, all right. So, 30th row all columns is going to be set at some value 10, all right. Just to see what we are doing at this stage, I will just use a command to see visually what we are doing. Image SE is a command that will allow you to look at a surface that you are defining. So, in this case we have a 2-dimensional matrix and I want to look at the values held by the matrix. So, image SE is nothing but image scale, it will give you an image, it is a 2D matrix and it will scale the color corresponding to the value stored in the matrix. So, as we run it you will be able to understand. So, I will just go to this button, save file and run, and I will run. Okay. I have this, right. Now, there are a few things that we need to look at, all right. There is some yellow color over here and there is some dark color on the remaining portion. I need to understand what color means what. Okay. So, I am going to go back to this code and place a command called color bar. This will allow me to figure out the values corresponding to different colors. So, on the right hand side, I have now a color bar appearing saying that the yellow color corresponds to value 10 and the darker color corresponds to value 0. Okay. The other thing that we notice over here is that the axis is very strange. The x axis goes from 0 to 30 and the y axis goes from 0 to 30, but from top to bottom. It is not the conventional way you draw the axis. So, 30th row has come down. I have a problem in visualizing this because the way we have drawn the diagram in the class is different and the way we are used to drawing axis is different. Simply because in image processing this is a conventional way of representing axis. So, we will go for some normal axis so that we can make a one-to-one correlation. So, I will just say in my command axis xy. It says that Octave can draw the axis in a regular xy graph, right. So, if I go now I have the line flipped. So, I have 0 to 30 on the x axis, 0 to 30 on the y axis, top row is set to 10 volts, right. Now that I have my preliminary setting clear, I need to write the code for solving the Laplace equation, that is all right. So, let us go ahead and let us say that I am going to open a while loop and I am going to say okay. So, this error what I am writing down here is going to be the difference between V now and V previous. If it is going to be greater than 0.1, I want to start a while loop, but before that I need to define what this error is going to be, right. So, the error that I wish to calculate is actually the difference between two matrices V now and V previous. The difference between the two matrices will also be a matrix, okay. So, now we have to figure out whether we want to take each and every point and compare, or whether we make some maximum error admissible in the entire difference matrix that you have got. So, the simplest way to do it is you take the difference between two matrices and you take the maximum element. But now the question is, since you are having V now minus V previous, it is quite possible that between the iterations there is a sign change. Maximum will capture only the largest positive number. It is also possible that you have a large negative number which is coming as a difference between the two matrices. So, we have to deal with the absolute value of the difference, right. In order to do this, I am going to say max, okay. Now, this is the slightly weird part of max. Max of max means that usually when we say max, it means that it accepts a vector, one dimensional vector, and it picks up the maximum element present in that one dimensional vector. When you have a two dimensional matrix, I have to use an octave max of max to find out the maximum in each column and maximum in each row, all right, and then give me a single value, okay. So, max of and I want to make sure that I am capturing both the positive and the negative signs. So, I am going to write down absolute value of V now minus V previous. Are you guys able to see what is being written? No? No? All right. So, I have the variable error defined as max of absolute value of V now minus V prev. V now is a matrix, V prev is a matrix. The difference between the two will give you a matrix, and I am going to use only the absolute value of all the elements. So, I have ABS, right, which will remove the negative signs, and then I am going to take the max of max. That is how we say that we get the single maximum element from the difference. So, while this error is greater than 0.1, that means if I start from line number 1 and progress towards line number 6, which defines the error, in order for me to write anything within this, the error has to be greater than 0.1. Right now it is, because I have made V now of 30 comma colon line number 4 to be equal to 10. Okay. So, if I just run this program, okay. So, it is an infinite loop because error is continuously greater than 10, does not matter, right. So, error is equal to 10, all right. So, it will enter this loop, and I would like to write the code for calculating the voltages within this loop. Okay. Now, for doing this calculation, I am going to go across each row, each column, and write down the average of the neighboring points for each of the points that I am wishing to calculate the voltage. Okay. So, I am going to start with for I equal to 1 to 30, okay, and for j equal to 1 to 30. The syntax here is, if I put 1 colon 30, 1 signifies the starting point for that for array variable or I, and 30 signifies the end point, and if I do not specify anything else, it means that it will go in increments of 1. So, it will be starting with I equal to 1, the next round it will be going I equal to 2, next one will be going I equal to 3, so on and so forth. If I want to specify specific increments, we can always do that, but in this course we are not going to be using any specific increments, always it is going to be units of 1, it is going to be integer. Okay. Now, I would like to write down the Laplace solver that we have already arrived at. So, I would like to take the value of the voltage at I comma j, which is the unknown quantity, and I would like to say that this is going to be equal to V now of I plus 1 comma j plus V now of I minus 1 comma j plus V now of I comma j plus 1 plus V now of I comma j minus 1, the whole thing divided by 4. So, very simple calculation, and you have your skeleton for your Laplace solution ready, alright, but there are some small niggling issues that we will have to fix. If we examine this line, alright, I start the loop at I equal to 1 and then j equal to 1, alright. So, I will be calculating V now at 1 comma 1, and it is now taking V now of 1 plus 1 comma 1, which is 2 comma 1, but then I have 1 minus 1 comma 1 also, which is going to index 0. Unlike C or C++, here the starting index in Octave or MATLAB is going to be 1. So, this is going to throw an array out of bounds or index out of bounds error. Okay. So, this means we need to start our loop at 2. Okay. The same thing is going to happen when it reaches 30, it will try to search for 30 plus 1 comma 1. So, it is going to become 31, so it is going to be index out of bounds of the array. So, we have to make this 29, 2 to 29, right. Okay. Okay. Now, at this stage, what has happened is 2 for loops will be executed for each row and each column, alright. And once this is done, I would like to calculate the error between the current value of voltages that we have found and the previous value of voltage that has been computed prior to starting this particular iteration. So, this entire for loop, 2 for loops will constitute one iteration. Okay. So, we make the error calculation once again. So, I am just going to copy and paste line number 6. Okay. Once I do this, it is going to remain within the loop, and I have to give some idea to what the V previous is going to be. So, V previous is now going to become equal to V now, because the next iteration will begin from the top once again, right. Okay. I would also like to have more information when we are doing this. I would like to know how many iterations it takes, alright. So, we can keep a counter variable. Before I begin the loop, I can say iter is equal to 0, and each time when I finish one calculation and make V previous equal to V now, I would like to increment this iteration counter. So, I will say that iter is equal to iter plus 1. Okay. Now, when you go from top to bottom within one while loop, within one iteration, you would have calculated the value of the voltages at all the points, and I want the system to display what has been calculated in every iteration. Okay. So, I am going to have a command over here which will allow me to do that, right. So, I am going to have image sc of V now. So, this is the command that we have over here. I am going to cut this, I do not need it there, right, and I am going to simply paste it over here. Okay. I am going to run this once. I immediately notice that there is a problem. I get the value of the voltages that have been calculated only after all the iterations have finished. Alright. This is a problem because the time it takes to refresh the screen, right, is larger than the time it takes to go for the next iteration. So, the CPU throws out the command to draw the picture on the screen, but before it attempts to draw, it has gone to the next iteration and it has completed all. So, it tries to keep on, the display buffer tries to keep on with what is happening with the CPU. So, we want to slow this down, alright. So, we will say that after every iteration, pause for a small amount of time so that I can have a look at what is going on. So, I am just going to put that pause 0.01. I do not remember the units of this pause command, maybe it is in seconds, maybe it is in milliseconds, but it seems to work. Okay. So, I am going to go ahead, do this. Now, I have something happening, right. Okay. There has been some calculations done, alright. However, I am not very satisfied because it is too little. I want to see the voltages that has been calculated, fairly more accurately. So, I am going to go ahead and say that while the error is greater than 0.01, reducing the error by factor of 10, right. So, I want to watch this slowly as what happens. The moment I get my cursor back in the command window, I know that the calculation is completed, alright. This is what the calculated voltages look like. Unfortunately, I really do not like this color scheme at all, alright. I would like to go for something else. I did not expect that the default color setting will be this. So, I will go ahead and change that, alright. Okay. So, I am just going to change this color map to jet, okay, little better. Okay. Okay. So, it is happening. If I want to terminate this abruptly, I can go to the command window and press Ctrl C. Alright. Okay. So, there you go, this is your preliminary. So, I will do this once again. Okay. So, this is the calculated voltage profile inside of a capacitor that is weirdly shaped. Okay. Let us go ahead and let us start to make some few more things that we can learn from this particular program, alright. First of all, I want to be able to do more than just draw the voltage values at each point. The course is about transmission lines and waves, alright. That means that we will have to learn about fields eventually, right. I would like to draw the electric fields inside of this capacitor and try to understand what is going on with it. Okay. So, I am going to go to the bottom. Once I have finished calculating the value of the voltage at each and every point, I would like to be able to draw the arrow plots of electric fields like how we do in regular class. Okay. So, the electric field here is going to be given by gradient of voltage. The gradient command takes the derivative of the voltages that you have calculated, but we know that electric field is minus gradient of voltage. So, after I do this, I will be multiplying each Ex and Ey by minus 1. So, I will just say Ex is equal to minus x, Ex, Ey is equal to minus Ey. Okay. And once I have calculated this, I would like to plot what the fields would look like. Okay. So, I give what is known as a quiver plot. A quiver plot is nothing but a plot that tells you, that gives you an arrow plot just like how you would draw in the case of fields. So, once you run it, you will understand what a quiver plot exactly is. So, I will keep my error fairly high so that it is lesser number of iterations. Okay. Okay. Now, I notice that I am getting some arrow plots. Okay. It shows that the arrows are emanating from the top and it is doing something and it has become very, very tiny. All right. I would like to have this plot on top of the voltage plot that we have calculated, and I would like to see really large arrows. The default setting is the size of the arrow tells you the magnitude of the electric field. All right. So, I would like to play with all that to get a preliminary starting point. Okay. So, what I am going to do is I am going to normalize the size of the arrows. So, I am going to say that Ex okay, is equal to Ex divided by x square plus . So, for each of the quiver plot I am calculating using the gradient of the voltage. I am just going to normalize the size of the arrow to its magnitude. I am going to make all the magnitudes to be equal to 1. So, this process I am normalizing all the electric fields that I am calculating. I will do the same thing for Ey. Okay. This is one part, and the other part is I wanted this to be on top of the voltages that I have calculated using this colorful plot. So, I am going to write a command saying hold. So, hold on allows me to take the last plotted graph and then add more contents to it using other. So, in this case I want to have a image plot of the voltage, hold it, on top of that place these quivers or the arrows for the electric field, right. So, I am going to run this. So, now I have the arrows appearing. Unfortunately, I do not like the color of the arrows in this computer. Default settings are all very weird in this computer. So, I am going to change this a little bit more, right. So, I am just going to write this down as maybe comma k. K is short form for draw it in black color. Okay. Okay. Now, I have the arrows starting from the top plate, all right, which depict the electric field. They are going downwards, and then there is a region where the arrows are not visible at all, right, or where there are no arrows that have been calculated, and then the arrows are terminating at the bottom plate, on the side plate, on the right side and the left side. There are a few things that we can notice over here, all right. One of the things that we can notice is the arrows emerge from the top plate at right angles, all right. The arrows are ending at the bottom plate at right angle with respect to the surface of the plate. On the side, the arrow will terminate at right angle, all right, both on the left and right hand side. This gives you an idea that the condition that we are looking at is a Dirichlet condition. The top plate is having a voltage of say 10 volts, okay, it's a source. The electric field is going to emanate normally from that surface. All the other plates are at 0 volts, so the electric field has to terminate normal to the surface. All right, in between it will curve, the electric field lines will not cross each other, okay. All these conditions are taken care of, okay. Now, just to be a little bit more clearer, I will make the error a little more tolerable. Okay. So, I am having arrows going to the bottom and then arrows going from the top plate to the left and the right hand sides. Okay. This is how one would solve a partial differential equation using a computer without having any general solutions plugged in. All you needed was definition of variables. You had some loops to cover different points, but remember that within those loops all you had was one statement saying that the voltage is going to be average of the neighboring points, and that kind of wrapped up how you would approach Laplace equation. All right. Now, the equations that we had seen in the prior classes for transmission line is a wave equation. It is a different partial differential equation, but its structure is close to the Laplace equation. It just has got some time derivative over there. We need to get there, all right. But before we get there, while we are on this, let us sort out one small issue with this simulation. When I began the problem in the last class, I was telling that we will start with a parallel plate capacitor, but now we do not have the parallel plate capacitor. It is a weird configuration capacitor. We can always go back and say, what should I do to get the fields of a parallel plate capacitor using this program, all right. So, one of the things that we can think about, all right, is looking at our algorithm itself and trying to figure out what can be done. Now, if we look at the calculated fields from the computer, we saw that the fields started from the top and went and terminated on the sides. In a parallel plate capacitor, you will not have the fields going to the sides, you will be having the fields going from top to bottom. Secondly, we have to assume that these capacitors are infinitely wide, so that the fields actually do not bend at all, they will go straight from top to the bottom. Okay. So, that means the fields have to emanate from the top at 90 degrees with respect to the surface, terminate only at the bottom at 90 degrees with respect to the surface. It should not curve and go to the sides. What is it in our program that makes it go to the sides? It is because we have assumed any unknown value of the voltage on the left and right hand side to be 0 volts. We have intentionally grounded it. So, when you have 0 volts intentionally placed, your field will try to get terminated on those plates. So, if we relook at our algorithm, the part we need to fix are the left and the right hand side boundaries. Okay. So, we need to look at these boundary conditions. Okay. Now, one of the things that we can do is relook at how else can I treat this boundary. Okay. So, we will start with the first point again. I have this value is say currently unknown and I have 3 points present. The fourth point is on the left hand side of this particular place where I want to calculate the voltage. It is not present. Okay. One of the ways to think about it is, suppose I have an unknown value of the voltage here. I can make that value equal to the value on the right hand side, that is I am going to have something like a mirror image of what this voltage is going to be. So, if I have an unknown voltage at the boundary, I am going to take the nearest neighbor and I am going to flip it or mirror it on this side, alright. I am going to have the same value of the voltage on the left side. Okay. When I go to the right side, the unknown value on the right side, instead of making it 0, I am going to make it equal to the point to the left of it. Okay. Now, that means that each and every time I encounter the boundary, the value of the voltage on the left and the value of the voltage on the right side of the boundary is going to be a mirror of what is there on the other side, which means that every iteration you are changing the boundary value, alright. It is a dynamic boundary condition, it is not a static boundary condition that you had before. But what does that mean? That should mean something, alright. If you place a boundary in such a way that the point that you are going to place on the left side is going to be equal to the point on the right side, and going by our previous lessons, if I want to take a derivative of the voltage along the x direction, since the voltage here is identical to the voltage here, the derivative of the voltage along that direction is going to become equal to 0. Okay. So, the numerical way of writing that boundary condition or analytical way of writing that boundary condition is dou v by dou x is equal to 0. Okay. So, when you go to the left hand side boundary, you will place something over there which is same as the value within the capacitor, and when you go to the right side, you will place that value equal to the value on the left, alright. That means that on the boundary you are imposing the condition dou v by dou x is equal to 0. This condition is known as the Neumann boundary condition, right. Unlike the previous condition, this is a dynamic boundary condition. Every iteration that you make will change your boundary condition, alright. And this is a special form of Neumann boundary condition where the right hand side is 0. It could also be any constant, but in this particular case we are just setting the derivative of the voltage with respect to x to be equal to 0. Now, I want to go back to the program and I want to fix the Neumann condition on the left and the right side, and then I want to calculate the fields of a parallel plate capacitor. Okay. So, I am going to go back to the program. I am going to close this, right. And I want to have a look at what I am doing over here, all right. So, it says that from 2 to 29 is my calculation, right, that happens. Okay. On the left hand side, right, I want to make some calculations. So, V now of colon comma 1 previously was not touched by your simulation. Once you started with zeros for all the positions of V now, you never altered V now at 1 comma something or 30 comma something. Similarly, you never altered x comma 30 and x comma 1, all right. Now, we are going to be altering that V now of colon comma 1, we are going to make it equal to V now of colon comma 2, all right. What we are doing here is on the left hand side, we are taking that there is going to be no derivative, that means that you are just going to make it identical to the point next to it, all right. So, we are just going to simply plug in the condition V now of colon comma 1 is going to be equal to V now of colon comma 2, which means that for all rows the first column the voltage is going to be that equal to that of second column, which makes dou V by dou x equal to 0. Same way on the right hand side, V now of colon comma 30 will become V now of colon comma 29. Previously, V now of colon comma 1 and V now of colon comma 30 were not touched by your program at all, but now you are explicitly setting them to be the values present in the last calculated values of the voltages. Okay. This is a simple way of writing the boundary condition. When people begin, they begin to write the boundary conditions within the loop, which is also perfectly fine. You can say that for I equal to 1 to 30 and j equal to 1 to 30, if I is equal to 1, you can write some boundary condition. If I equal to 30, you can write another Laplace equation solutions, or we can say that if j is equal to 1 or j is equal to 30, you will have another statement which will tell you what V now should be equal to. So, one of the ways you could do is V now of I plus 1 comma j multiplied by 2 plus the remaining terms, right, because you are taking the value on the left to be equal to the value on the right, you are adding it 2 times. So, you can always do that. So, this is a simpler way of writing the same boundary condition, right. So, I am going to do this once again, I am going to hit run. Now, I suddenly notice that the voltages are appearing as straight lines. There is no derivative of the voltage across the x direction, and the voltage is linearly changing from 10 volts to 0 volts at the bottom, all right. And my fields are absolutely straight going from top to bottom. The fields do not curve or do anything. They do not have ground plates on the sides. Also, we are considering that there is no derivative on the x side, which means that it is infinitely large and there are no fringing fields or fringing capacitance present over here. Okay. So, this would be the definition of Neumann condition. I am not sure how many of you have solved partial differential equations before on a computer, okay. But by looking at this, I hope you will be convinced that there are some merits, all right, in doing it in this way, because visualization becomes easier than actually writing down a few analytical solutions. So, in this class we will not disregard analytical solution or use only numerical values, etc. We will try to go hand in hand. Each time when we encounter a partial differential equation system, we will try to identify first what is the unknown in the equation. Next, we will try to figure out how to represent unknown in terms of known quantities. Third thing that we will do is figure out an algorithm to calculate the unknown quantity using some iterative method. The fourth thing that you will do is you will try to figure out the boundary conditions, what you need, all right. And fifth thing is write the program and just run, and then try to make derivations of what is going on, physical interpretation of what is going on. Now that you know how to solve Laplace equation, we need to go back to our equations that we had derived before, which was the wave equation, and try to write down how we are going to solve that. So, let us go ahead and do that now, and we will wrap up our class once we get the expression for the value of voltage in the case of wave equation that we had derived in the first or the second class. Okay. So, I will go back to my notes. So, I have the wave equation for the voltage and the wave equation for the current. I am going to take the wave equation for the voltage. Dou square V by dou Z square is going to be equal to 1 by u square dou square V by dou t square, right. So, I am going to take this and I am going to start to figure out what is the unknown in that wave equation, what is the known quantity, how do we find out the unknown quantity. Okay. So, I will write this down once again. Dou square V by dou Z square is equal to 1 by u square dou square V by dou t square. Now, we already know how to represent second order partial derivatives using the Taylor series expansions that we have got before. Dou square V by dou Z square, alright, can be written in terms of Taylor series. So, let us go ahead and do that, alright. Here, let us note that there are two independent variables. Okay. Okay. I need to write down dou square V by dou Z square. So, I can go back and I can try to find out what the second order partial derivative of a function would be. So, I had dou square V by dou x square to be this particular expression. So, I am going to just use this expression on the left hand side. So, I have V of z naught plus delta z comma time, right, plus V of z naught minus delta z comma some time minus 2 times V of z naught comma time is equal to 1 by u square. U is the velocity, has to be known, right, and on the right hand side I will be having V of, okay, let us make this T naught to be consistent. So, T naught, T naught, T naught. Okay. On the right hand side I need to take the derivative with respect to time, alright. So, the spatial coordinate would remain at z naught, I will have T naught plus delta t. Okay. I think I need to put the denominator on the left hand side, right, divided by, it should be delta z square. Okay. So, I will just V naught, V of z naught comma t naught plus delta t plus V of z naught comma t naught minus delta t minus 2 times V of z naught comma t naught, and there is a denominator present there. So, I am just going to pull this denominator here and then write this down as 1 by delta t square u square, the expression on the right side. This is how I would approach the wave equation. Okay. Once you do this, you need to identify what is the unknown. In all these problems, there are some simple ways of estimating what is the unknown, alright. The simplest guideline that I can provide is in the wave equation, the right hand side is a derivative with respect to time, and if you look carefully on the right hand side, you have voltage to be found at t naught plus delta t. If you assume t naught to be the current instant of time, t naught plus delta t is going to be what is the value of voltage at the next instant of time. Okay. So, in cases of equations which have time derivatives, the unknown is simply the future values, alright. So, from this equation what you are supposed to do is take V naught of z naught comma t naught plus delta t on one side, all the other quantities on the right side. If all the other quantities are known, then you will be able to estimate the value of the voltage V at position Z0 at the next instant of time. So, we are saying that if the past values T naught minus delta T is known, if the current values voltage at T naught is known, then you will be able to estimate what is T naught plus delta T. It requires a rearrangement, alright, and then once you rearrange, you will need to plug in a few values, right. So, for starters, just like how we did Laplace equation, you can say that delta z and delta t is going to be equal to 1. That is how we did delta x and delta y in the case of Laplace equation. And u, the velocity, we can take some 1 meter per second or 1 grid cell per unit time step to make our calculations very simple to begin doing this analysis. So, we will stop here. My suggestion is try to bring the unknown to one side, known quantities to the other side. Keep your equations ready. In the next class, we will write a code for this and then try to understand what the wave equation that we derived in the first two classes actually meant. What are the boundary conditions for the wave equations in transmission lines, alright, and then we will proceed from there. Okay. So, I will stop here.